Hello, I'm Kartik Goyal, and today I'll be describing our work on a model for analysis of the visual appearance of printed characters in early modern documents. Many bibliographic studies that focus on discovering the origins of secretly printed books rely on the visual appearance of the individual character imprints in those documents. For example, these studies might focus on subtle differences between different fonts of the imprints, or they might also focus on the unique damages that occur to the metal casts during printing. We propose a model that clusters these collections of imprints on the basis of very subtle differences in their fonts. Consider this collection of Fs. Ideally, the clustering of these Fs would be the top row would be one cluster and the bottom row would be another, which is based upon the glyph shapes, with the top row having the long middle arm, and the bottom row having a short middle arm. However, we can see that these Fs have other confounding sources of variation, which are probably more dominant and might throw off conventional clustering algorithms like k-means or structured variational autoencoders and result in undesirable clusterings. We ameliorate this problem in our model by using interpretable latent variables to isolate the important sources of variation that are useful for clustering from the confounding sources of variation that are still important to model, but they are modeled by non-interpretable and flexibly neurally parameterized latent variables. Specifically, in our model, we first choose from among many different template shapes, in this case 2 here, one of the template shapes with the latent variable C, and in this case we chose template T2, and we basically describe how this template undergoes a series of transformations with both interpretable and non-interpretable latent variables to explain the final observation X. It should be noted that these template parameters themselves are learned during training, and the first step is that they get warped by the inferred interpretable latent variables. These interpretable latent variables lambda are basically spatial adjustment variables, which account for slight rotations or translations or scale and shear differences caused due to the inherent noise associated with the typesetting process in early modern printing. It should be noted that the warp operations themselves are deterministic and differentiable. And also the latent variables lambda are all continuous, which is in contrast to previous work which discretized these latent variables. Now we use the latent variable z to account for other sources of variation like inking effects or noise due to archiving effects. And basically the z operates on the template t tilde via a neurally parameterized function called filter to further transform the template to t hat, which defines pixel-wise Bernoulli probabilities from which the observation can be explained. The learning happens by maximizing the likelihood, but the log likelihood has 2 different marginalizations, one for interpretable, one for non-interpretable. For the interpretable latent variables, we define a lower bound via iterated conditional modes, which converts the problem of marginalization over lambda to maximization over the variational parameters. And this maximization can be performed by stochastic gradient methods. We define a further lower bound approximation for z by associating an auxiliary distribution Q with it that is parameterized by a neural inference network. The final objective function looks very similar to the familiar elbow function, which is commonly used for variational autoencoders with this Q of z. Now, as we mentioned earlier, we desire Z to capture the sources of variations that are not captured by the interpretable latent variables. Therefore, the inference network, while training, instead of getting access to full image X, gets access to a residual image where the warped template is subtracted from X and passed into the inference network from which Z can be sampled. First, we analyze the performance of our model on fitting the data itself. In the blue are the models with only the interpretable latent variables and no neural components. And in the red are models with some neural component. And we see that the neural models are much better than non-neural models at fitting to the data. But when it comes to the clustering performance, we see a particular pattern. Our model still outperforms all the other models, but the MVA model, which is a neural model, performs much worse than even the non-neural models. This MVA model is basically a simple structured VA model that has been used for semi-supervised classification over MNIST digits. This shows that just being expressive is not good enough for defining useful generative models. We used our models for qualitative analysis as well. We ran our model on 25 Ornaments Leviathan, whose origins are disputed, and our model was able to learn two different fonts for Fs and Rs. For Fs, one with short middle arm and the other with long middle arm, and for Rs with two different legs. So we proposed a model for typographical analysis of early modern printing, which is both interpretable and expressive. Thank you.